All right, so today what we are doing is we're just going to be kind of picking up from where we left off. So if you remember last class, we kind of covered up to the descriptive statistics. So we were looking at like mean, median, mode, and what kind of importance they have in terms of research methods and in terms of the results of an experiment. So today we're going to extend on statistics a little bit more. And we're going to be looking at a specific type of statistic that we use to try to understand differences in results, or try to understand the spread of results, okay, or the range of results that we might obtain from a study. So this statistic that we're going to look at today is called standard deviation. Now, this should not be a new term for any of you, because for those of you who do maths now, or even in up to year 10, you might have come across this word standard deviation. Standard deviation is related to our normal distribution in maths. And the normal distribution basically plots the mean right in the center, and then you've got the results lying on either side of that mean value. Okay, but we don't need to go into the mathematical specifics of it all. We just need to be able to define standard deviation as displaying or demonstrating how far the scores within a set of scores are actually spread out. So if I've got a bunch of scores or a bunch of results from different participants, I can plot that as a graph, obviously. I can plot that according to a normal distribution. So some of you might be within the normal level or within that mean range. Some of you might be above that range. Some of you might be below that range, okay? And some of you might kind of be just above or just below, okay? Some of you who are extremely good in the subject might be extremely above, okay? Some of you who might be really poor in the subject, or maybe who left everything blank, you might be extremely below average. Okay, so basically what we try to say is that when we're talking about the standard deviation, we have to acknowledge that there is a mean, value there. Oops. Okay, I'm just trying to do something stupid now. It's not working, I think. Yes, there we go. So there is a mean value, okay, and the mean value is our typical value. We learned about mean values last time as being our typical values, okay? That's the average. Right, if we did a SAC and the average score was like 62%, that would be the mean. Now, on either side of the mean, you've got other values, okay? You don't need to memorize these percentages, but this is just to show you what the general standard deviation is about. Now, if we've got someone who's extremely below average, who probably just wrote their name on the SAC, answered a few multiple choice, and just handed the SAC in blank, they might be somewhere around here. Okay, which means that they might be 2 or 3 standard deviations away from the mean, okay, on the negative side. If we've got someone who's done extremely well, who's studied so hard, and who's answered every question, and it's completely, their answers are completely impeccable, like I cannot even pick a single flaw in that, and they get, let's say, 97 or 98%, then they will be on the upper hand here, okay? We can't expect every student to get 98%. So they will be represented by a very small percentage, okay? Maybe 2 or 3 standard deviations above the mean value. So essentially, when we're talking about these values here, all of these values here represent our above average, above mean values. All of these values here represent our below mean or below average kind of scores. Okay, now with any kind of investigation that we do, we are able to basically plot or put our scores into a graph like this, okay, or represent or display our scores on a normal distribution with reference to where those scores lie in relation to the mean, in relation to the in relation to the average. Okay, I was trying to say average and value at the same time. Okay, yeah, so in relation to the average, we can then see where the actual score lies on that normal distribution. Now, normal distributions are extremely important, okay? We use them to make sure that we have a standardized measurement in which we can measure results. And this is very important because it ensures that there's no bias. It ensures that participants do not have an unfair advantage, and it ensures that the researcher cannot favor one group over the other because the scores speak for themselves when you put them on the normal distribution. Okay, if we relate this back to kind of real life, your ATAR scores, for example, study scores, they are all mapped out in terms of like you can map out any performance of any subject on a normal distribution. And if you ever access like the statistic reports, which show you, for example, how much you had to score in 2019 to get A+ on the exam, you will notice that they actually have graphs there for you. Okay, and those graphs will actually show you what the mean score was, what the average score was for psych. It's usually about 27 or 28. It'll show you the median value, and it will plot a kind of graph where it does look like a normal distribution and show what range of students got in the lower grades, like E+ or E or D, and which students got in the higher grades, like A+, A, B+. And in the mean, you'll see that the mean is usually about a C+, so that's right in the middle. Okay, so we can plot any kind of score on a normal distribution or mean graph. And in order to do that, we have to make sure that we've got this standard deviation, this standardized statistic or this standardized measure, which allows us to ensure that we can understand the results and not just take the mean value or the average value by itself, okay? Because as I'm going to explain in the next slide, the mean value does tell us a lot. It tells us the typical value, it tells us the typical performance of that group or the average performance, but it doesn't tell us the little biases that might have kicked in. It doesn't tell us the little confounding variables that might have led to a larger spread of results. So I'm going to go through that a little bit more in the next slide. But before I do that, I just want to tell you guys that obviously a low standard deviation means that there's little variation, there's little differences in the score, and that most scores are clustered around the mean. So if we look at a low standard deviation, most of the scores will be around the mean. It will be kind of like mostly in this area, okay? That would be a low standard deviation. The spread would be very small. It's not spread out. Whereas if you've got a high standard deviation will be more spread out, which means that the variation among the scores and the amount of actual spread that the results show from the mean value is higher. So you might have results that look like that. The mean value is here, but the results are a lot more spread out compared to that maroon or burgundy colored scribble there in the middle, okay? So low standard deviations means little variation in the scores, and this is what we always want. We don't want our scores to vary completely, but in some cases it happens, okay? There's no stopping it, and that could be because, again, individual participant differences exist. Every year we will have a kid who will get, you know, really high score, and we'll get a kid who gets like, you know, 20 or 22 or 19 or 18, like lower than the state value or state average. So it happens in every classroom, in every school, because we've got students who are of differing abilities, okay? We've got everyone, and some people have different motivations for the subject. Some people have different kind of effort that they put in, different kinds of you know, goals. One student might come into the subject being like, you know what, miss, this was my 6th subject. I had a student like that, like in a previous year, who actually came in and told me, miss, this is my 6th subject. And I knew that they were capable, but because they'd come in with that motivation, they kind of set themselves up to not perform to the state average, even though it would have been very easy for them to do so. Okay, so again, we have to remember that whichever experimental group, whichever group of people or participants or cohort you are testing, you will have individual participant differences. And these differences are what often lead to a wider spread of results, okay, which don't just allow us to have the results confined to one small area there. Okay, so that's basically what standard deviation is. And in this graph on the right here, you can see this is a little bit more easier to understand. So you've got standard deviation 0, which means that everyone has scored exactly the same score, which will never happen in any classroom because everyone is different. 0.5 is a very low spread, it's a low number, but you can see that when we come to this, I don't know if you guys can see this properly, when we come to this particular one here that I'm just drawing over, this is a standard deviation of 2. So you can see that it's a lot more spread out as compared to the standard deviation of 0.5, which is very little in terms of its spread. Okay, so the higher the standard deviation, in other words, the higher the spread or the higher the variation in those results. Okay, so going back to, going to the next slide, sorry, whoops, what have I done? Okay, there. So going to this example now, I've just literally copy pasted this from your textbook. I think it's a really good example, so I just thought we might as well put it in. And on top of that, I know like most of you guys don't like to read through the textbook, especially because sometimes there is a lot of detail in there. But this is a good example, okay? So I'm going to try to explain this in the context of, you know, our classes. So suppose that 2 psychology teachers discuss the abilities of their respective classes. So let's say Miss B's class, Miss B was talking to me and Miss B was like, okay, the mean score for the students in the Unit 3 Outcome 1 SAC for her class was 78%. So she's like, Farine, the average score for students in my class for that first SAC was 78%. And I was like, all right, cool. My class, the average was 68%. Okay, just an example. So obviously I tell her it's 68%, and I'm thinking in my brain, you know what, maybe my students are not as capable as Miss B's students. So then what's it called? We kind of start to discuss, okay, maybe it's about the marking, okay? So obviously Miss B might say something like, okay, one of my students got 97%, but on the other hand, another student who was in the same class got 18%. So you can see there's quite a bit of spread there, yeah? A bit of variation or difference in terms of the scores that Miss B's class has received there. And class B teacher, which is me, I'm like, okay, well, that's surprising because the lowest mark in my class was 53%, but the highest mark was only 81%. But you can see there that even though the highest was only 81%, the lowest was 53. There's not much spread there. The difference is quite low in terms of the difference between those two scores compared to Miss B's class, okay? 97% and 18, that's a huge difference. 53 and 81, still kind of a big difference, but not as much. Okay, so now me and Miss B are kind of standing there and we're confused. Okay, how do we know which class has the better abilities now? Okay, so obviously this example here, which is just taken from your book, is trying to show you that just simply stating a mean value is not enough. It doesn't give you the whole picture in terms of the data. And this is why it's important for us to also use standard deviation so we can understand that it's not just about the mean value, but about how much the scores vary, how much the scores differ in that specific experiment or in that specific class or in that specific subject cohort or subject group of students. Okay, so obviously this is why the standard deviation is used to understand what kind of spread we are seeing in terms of the results. Are we seeing a big difference in results, or are we seeing a small difference in results? Ideally, we want to make sure that our results are not as spread out, but again, it can't always be like that, okay, because of individual participant differences. So again, you have to realize that the mean is the same for class A and class B, but for class B, the scores are a little bit more spread out, whereas for class A, the scores are a little bit more tightly bound or kind of packed together. Okay, so obviously, because class B has a higher variation, we say that class B has a higher standard deviation as well. Okay, standard deviation simply measures the spread of results. Okay, so standard deviation, whenever you see that word, you have to remember that it measures the spread. Wow, I write so nicely with this ugly pen. Okay, spread or the variation of results. Spread/variation, okay? And remember that the standard deviation, or why it's so important for us in psychology, is that it gives us more meaning to the results. It tells us a bigger story to the results that we would not be able to understand with the mean value alone. So in other words, the standard deviation kind of elaborates upon what the mean already tells us and makes us understand the spread of results, okay? So that's basically what standard deviation is about and why it's important. Remember, you'll never be asked to calculate a standard deviation. You're never going to be asked to draw a standard draw what two standard deviations from the means looks like. It's just simply you understanding the significance of standard deviation as a statistic in psychology. And what the significance is that it supports the mean in giving us the whole picture and the complete description of the data, helping us to understand the level of variation in the data, okay? Because it's always important for us to make sure that our results are mostly within the same range, okay? If we've got a really massive range, there might be other variables at play. And I'm just gonna go back to the previous slide to just show you, oh my God, what am I doing? Back to mouse. Ah, there we go, finally. Okay, so basically what I mean by we always want to make sure there's not too much variation is that if most of my students have got a result, oh my God, what am I doing? I should just not ever use a stylus, literally. Okay, okay, so if most of our students end up getting a result end up getting a result that's on either side of the mean, okay? One standard deviation to either side of the mean. So if the mean is like 60 they get either in the 50s or either in the 70s. That's fine, because that's showing me that there's not much of a spread. If, however, in the same class, the majority of students get in this range of results or within this boundary, but then suddenly I've got 2 or 3 students who have got in the very below average thing of 3 standard deviations on the negative side or on the away from the mean, then that's a problem. And I have to ask myself, okay, why did those 3 students get so low when the majority of my students actually did okay, or actually got, you know, just 1 standard deviation away on either side of the mean? Okay, so it's always important for us to investigate those, because they could be outliers, they could be potential confounding variables. Like maybe these students missed out a lot of class, so we can't actually take their results into consideration because they didn't attend half the classes. They were sick, they were at home, they had other extracurricular stuff that they were pulled out of class for. So before I do my study, I need to account for these students, because if I don't account for them and withdraw them from the study, from taking part, they will eventually go on to make my results look really funny, where all my other students are in this range, and then I've got 2 or 3 that are the odd ones out on either side of the mean. Okay, so that's basically showing you why it's important for us to have mostly a consistent variation there, okay? But again, like I said, in real life, it's not always possible. Alrighty, so if everyone is all good, I can just keep moving on. But if you have any questions about the standard deviation, just ask me at any point. All right, the next thing that we're going through is called reliability. Now, when we're talking about reliability, it's important for you to remember that reliability is about the results, okay? It's about basically looking at whether the results are essentially reliable. Can I actually rely on these results? Are these results something that can be used to inform future research, okay? So what reliability is it's basically talking about the fact that our results need to be accurate, okay? Our results need to, if we do a study again and again and again, we need to be able to get the same or this very similar level of results each time, okay? And there's a memory tip that we use for this as well, which I'll come to in a second. But the definition, or the textbook definition for reliability, is that reliability refers to the extent to which the results obtained from a research study or experiment are consistent, are dependable, and are stable. And we use this memory tip CDS to remember that. So the memory tip, which is obviously written here on the slide, is that if I have, it's kind of like trying to put an image into your head, okay? So I don't know if you guys will get it at first, but the memory tip is basically like a little kind of saying. So if I have reliable CDs, I will use them over and over again, and they'll give me the same quality of results each time. So back in the days when we used to watch DVDs and we didn't have Netflix, you know, I don't know if some of you would remember, but if a DVD got scratched in between you watching a movie once and you watching it the next time, if a DVD got scratched somewhere in the middle because your little sister took it and was playing around with it or something, you wouldn't get the same quality of that DVD the next time you watched it, okay? That's similar. You can kind of use that analogy with results in research as well. If I do a study, let's say if Pavlov did his study on dogs and salivation in response to a bell, if he did his study once, he can't just say, oh my God, yes, my study is 100% reliable, the results are reliable, everything is all good. Because he has to then be able to replicate that research and get the same results or get similar results again. If his dog salivated when hearing a bell in the first study, but when he tried to redo that study again, they didn't salivate in the second trial or in the second attempt of that study, then his results are not reliable. They might have happened off chance, okay? They might have happened just by sheer luck or just by sheer coincidence. So we have to make sure that when we do conduct a study, the results are reliable, and that when obviously you conduct the same study again, or another researcher wants to replicate your study or redo your study, they will get similar results each time. It doesn't have to be, the results don't have to be identical, but they do have to be similar, okay? The quality of the results or the actual findings do have to be similar. They cannot be something completely different, because then that suggests that your results are not reliable. So reliability, use that memory tip of CDs, that if you've got a reliable CD, you can use it over and over again, expecting the same quality and results each time. That's exactly what reliability of results is talking about. So obviously consistent repeatability of a study equals to reliability. If I am able to consistently repeat a study again and again and again, I'm able to consistently repeat an experiment again and get the same results or similar results each time, that equals to reliability of my results. Then I can conclude that yes, my results are quite reliable. Now, why is this so important? Why are we beating around the bush so much about, like, you know, results being reliable, being consistent, being dependable, being stable? Well, number one, if I, for example, do attempt number one of a study and I get some results, and in attempt number two, I don't get those results again, it's suggesting that the results that I got in my first study might have not been due to the IV at all. They might have been due to extraneous or potential confounding variables that I did not account for. And obviously, if I'm getting different results each time I conduct the exact same study in the exact same circumstances or conditions, then that's a little bit unreliable in the sense that something else is at play. There's some other chance factor, there's some other variable at play, and this is going to affect my ability to generalize results. So regardless of whether I use random sampling in the study, regardless of whether I design the study in the best way possible, if I don't have reliable results that can be replicated and still be similar each time, I am not going to be able to generalize my results. So think about reliability as kind of like hitting a target, okay? Each time you draw one of those arrows, that's attempt number, oops, sorry. So that first, that first arrow there might be trial number one of the study. The second arrow there might be trial number two. The third arrow might be trial number three, okay? Each time I conduct the study, I'm hitting the target in almost the same area. It's not exactly the same point because obviously they are sitting there at different kind of locations within the same target there, but again, it's a similar, okay, similar results each time. The results are not vastly different. It's not like one arrow is in this part and one arrow is here and then one arrow is somewhere in the middle here. No, they're all within the same target there, okay? So that's basically what reliability of results are. Reliability equals to CDs, consistency, dependability, and stability of results. Okay, the contrasting concept for reliability now, or not contrasting, but similar thing that we always need to make sure our results are, is valid, okay? Validity is the next thing that our results have to be. Validity is basically a simple concept. It's basically explaining that the procedures or the tools that are used in a research study need to measure what you want them to measure, or need to measure or assess what they are expected or created to assess. So if I'm going to give you guys an example, obviously nowadays there's always like a big thing about high protein diets and all that stuff. And when we're talking about high protein, just one, okay, is there a general number of attempts you need to conduct? No, there's not a general number. As long as like let's say you try your experiment or you redo your experiment maybe 3, 4, 5 times, as long as you're getting the same results, then same or similar results, then it kind of suggests that you do have a reliability there. Okay, there's no magic number involved. Again, famous studies, like if we look at Pavlov's study, oh my God, Pavlov's study has probably been replicated by researchers everywhere since it was published, like in the late 1800s. So he probably has like thousands, hundreds of thousands of people who have redone his study and got similar results. And that's why we study his experiment, because it is so reliable. The results from that study are so reliable, okay? Everything that we study in psychology as a classic study or as a classic experiment, they have been replicated in some way or the other again and got similar results. So coming back to validity, validity is again, whether the procedures or the tools or the measurements that we use in a research study measure what they are intended to measure, okay? So this is basically talking about the fact that if I am measuring weight loss as a dependent variable, I need to have a properly functioning weighing scale. I can't have a scale that measures 5 kilos above or 5 kilos below, because that will lead to improper results. In that case, my measuring device is not actually measuring what I want it to measure, okay? So obviously when we're talking about other things here, when we're talking about like a study, okay, there's been a lot of discussion about the whole keto diet and eating high protein, high fat in terms of fat loss. So obviously if we're measuring the impact of high protein diets on fat loss, but we have a weighing scale that is inaccurate or malfunctioning or shows a different number of kilos than what you actually are, then we will say that the results we get from that study will have low validity. They have low validity because the procedure or the tool that we used, in this case, our weighing scale, does not measure what it was supposed to measure. It does not measure what you intended it to measure, okay, in the correct way. And for this reason, any kind of results that we get from this study, no matter how well we set the study up, will have low validity because the machine that we used to measure those results in the first place was not working properly, was impaired, was malfunctioning. In the same thing, the example they use in your textbook is that if you're trying to measure like waist circumference, okay, you're trying to measure someone's waist circumference, you usually use one of those tape measures. And back in the olden days, they had cloth tape measures, which were made of like cloth or fabric. And they were saying in the book that if you were to take that cloth tape measure and put it outside, because it's cloth, because it's fabric, it will kind of constrict once it's exposed to heat, okay? And it will become a little bit less stretchy or less kind of like wide in terms of its length. And so when you use that to then measure someone's waist circumference, you are either going to over measure or under measure their actual waist circumference. So in that case, that tape measure, which has been left in the sun and has become a little bit shorter in length, might not be a valid measurement of someone's waist circumference, okay? Because the tool itself or that procedure that we use has now become impaired in a negative way or affected in a negative way. The validity of a study is important because it does actually affect the ability to whether a researcher can make a correct and accurate conclusion, okay? And obviously, because of that, the validity of our study is influenced as well by whether the researcher's conclusions are correct to begin with, okay? And the validity of a study can also be influenced by whether we've got too many potential confounding variables. So if we've got a few individual participant differences, we've got some non-standardized instructions and procedures, and we haven't controlled for these, then this can obviously lead to the study having low validity as well. It's not always simply about the measurement tool not working. That is the main example, but it's not always just about that. So if you get a case study, but all the measurement tools are working fine, the weighing scale is working fine, nothing seems like it's broken or impaired, look at whether there are potential confounding variables, okay? Look at whether there are you know, some kind of conclusions that the researcher has made that seem a little bit far-fetched or that seem a little bit too overconfident or absolute, okay? So obviously we're looking at those characteristics as well. It's not just always about the measurement tool that was used. Now, obviously, in this sense, if a researcher does draw an overconfident conclusion and you're like, wait a second, that conclusion is a little bit far-fetched because the results say one thing, but then this guy is concluding another thing, that could again indicate that your results have low validity because the researcher might have actually drawn a conclusion that's not based on the actual results. Remember, whatever conclusion you make, you have to make it based on your results, okay? That's why we say in the discussion section of any paper, the results, the hypothesis was supported by the results, or the hypothesis was not supported by the results. We can't draw any conclusions about the hypothesis being supported or not supported unless and until we look at the results and analyze the results accordingly. We can't just make up a conclusion out of thin air, okay? And if we do make a conclusion up out of thin air, then our results automatically become invalid. So there are two types of validity that the book goes through. Internal validity and external validity. So internal validity is basically everything I just talked about now. It's when the results that are obtained from a study might not actually be due to the IV, maybe some extraneous or potential confounding variables have come into play. Internal means internal, so it means inside the study. So internal validity is referring to factors within the study or inside the study that have made our results not valid. External validity is again outside, okay? External means outside. So external validity is referring to the extent to which our results might be generalized to the outside population. Again, both internal and external validity are influenced by potential confounding variables. Remember, we said potential confounding variables are really sneaky things. They always get into affecting everything in a study. And validity and reliability are prime examples of what they can affect in terms of the results, okay? So if you've got potential confounding variables in your study is very highly likely to be unreliable and very highly likely to be invalid in terms of the study's results. Okay, so that's basically what validity in research is about. Okay, it's about measuring what we're supposed to measure in terms of measurement tools working properly, in terms of conclusions being based on results and not based on just stuff you make up, and in terms of controlling for potential confounding variables and extraneous variables as well, if there are any. Now, looking at this diagram up here, this little target thing, this is showing you what reliable results look like if they're invalid. So you can see that all the results are within the same place, but they're not hitting the target. And that's not something we want to see, because we always want to make sure the results are hitting the target and that they are reliable. So in this case, reliability is shown, but we don't see, for example, validity in that first example there. In this second example here, you can see that the results are reliable because each time we replicated or redid the study, the results are in the same location, and it's valid because it's also kind of within that same range there. Okay, it's valid because every time we conduct the study, the results are measuring what we want them to measure. So as long as we see our results always hitting that target of both being reliable and being valid, then basically we have achieved our goal of getting valid and reliable results. Because you can have one without the other, and I'm going to show you guys a super confusing kind of saying for that on the next slide. You can have one without the other, but if we can have both, that is always the best case scenario. So the last slide we're going to go through today, before we finish is just kind of summarizing that previous picture I showed you. And I call this slide hitting the target when it comes to reliability and validity in research. So obviously this is the saying that is super confusing. A measure can be reliable even though it is not valid, but a measure cannot be valid unless it is reliable. Okay, so that's super confusing. What it actually means is that I can use, let's talk about the example with the weighing scale, okay? The weighing scale is 5 kilos off. If I get participant number 1 and they weigh 75 kilos, but the weighing scale is 5 kilos, it shows 5 kilos below your actual weight, okay? So this guy comes up to me and he's like participant number 1 and he's like, okay, I'm ready to check my weight. He steps on the scale, and this 75 kilo guy, when he steps on the scale, he is 70 kilos on the scale, okay? What the first part of this saying means, that a measure can be reliable even though it is not valid, is that every time I ask that guy to step on the scale will always show 70. It's still showing the same number or the similar number each time, even though it is not valid. Even though that number is wrong, it's still showing me the same number each time. So I can say that that weighing scale is an invalid measure. It's not valid, but it is reliable because it's still showing me 70 kilos each time, okay? But a measure cannot be valid unless it is reliable. So I can't use a measure each time and expect it to show the same results unless that measure shows me the same results each time I use it, okay? So if this guy steps on the scale and one time it's 70, the next time it's 82, the next time it's 92, I'm gonna be like, what on earth is this scale doing? I just have to chuck this out the window because this scale is not reliable. It's not showing me the same results each time. And for that reason, I cannot expect to use this as a valid measurement at all. Okay, so that's what we say when a measure can be reliable even though it's not valid, but a measure cannot be valid unless it is reliable. Okay, so these are just some little target diagrams I've just found on Google Images. The one that we're concerned about is the last one here. So looking at the validity and reliability part. If I can change my color. Why can't I do that? Yes. Okay, so valid and reliable. So obviously we can see here that our results hit the target, okay? They hit the heart of the research aim. When they hit that area, they are basically supporting the hypothesis because the results are both reliable. Every time I did the study, I got similar or the same results, and the results are valid. So the measurements that I used to get the results worked. They worked properly, they were not wrong, and there were not any major potential confounding variables that might have affected their performance. Okay, so obviously that's what we always want to see in terms of a diagrammatic representation of validity and reliability. We want to see the results being clustered in the same area, not like the first diagram here where everything is spread out in random places, okay? This shows obviously very unreliable and very invalid results there, okay? Because nothing is in the same place. Everything is spread out. It's like, where do I even look? Everything always has to hit the target in one spot in order for the results to be valid and reliable. Okay, so that's basically all we're covering today. I'm not going to cover more than this because I know these topics can be a little confusing. Just remember, reliability refers to CDs. Okay, we wouldn't refer to a CD as being valid. We would refer to a CD as being reliable, right? So obviously, if I've got reliable CDs, I can use them again and again and expect them to give me similar results each time. Okay, and validity is about, okay, is the measurement valid? Does it work properly? Does the weighing scale work properly? Are there any potential confounding variables? Okay, so they're two different measurements, but a lot of the time students do get confused with them. If you still are a bit confused about them, I'm happy to explain them a little bit more, either today or once we get back to school. Alrighty, so that's about it for today. So what I'm just gonna do is I'm gonna see if Schoolbox is working. Oops, okay, minimize. Yes, okay. Okay, I know the screen has probably gone blank for everyone, so let me just reopen that. Okay, so, and what I will do is I will stop the PowerPoint here.